Hi, my name is Amos Tversky from Stanford University, and today's lecture deals with the topic of measurement inequalities. In the systems of measurement that we have considered so far in the lectures, we always employed a solvability axiom of one type or another. In the context of extensive measurement, we have assumed that if A is larger than B, say if A is heavier or longer than B, then our object set is rich enough to include an object C such that A matches the combined effect of B and C. In the context of conjoint measurement, we have assumed that our two factors, A and P, are so arranged that we can solve equations of the form A2 P0 matches A1 P1. In general, solvability axioms are essential to the construction of the scales that we have developed so far. However, in an important sense, they are of course not necessary, because in the measurement of mass, for example, it is quite possible to obtain an additive scale of mass even if we cannot find a C that matches such that its combination with B will match the effect of A. Similarly, in conjoint measurement, we may find additive representations for various structures, even when one of the factors or more are discrete, so such equations could not be solved. It's important to realize that in some sense, solvability axioms in their various forms are innocuous. They only require that certain constructions could be carried out. They don't impose constraints on the nature of the solutions. Nevertheless, imposing a solvability axiom introduce several problems of both practical and theoretical nature, and the purpose of today's lecture is to investigate what happens when the solvability condition is eliminated and to obtain necessary and sufficient condition for measurement structures without this condition. In a way of introduction, let us examine the role of solvability in conjoint measurement. Consider, for example, a two-factor structure described here with factors A and P. And one possible interpretation will be to think of that as a space of commodity bundles, where A correspond to one commodity, say leisure time, and P correspond to another commodity, say money. The normal constructive procedure for scaling such a structure is based on taking a starting point, A0, P0, as our origin, finding a level P1 on the first factor, so that the combination A0 P1 matches the effect of A1 P0, and then constructing further points along the space by solving equations. When we proceed in that way, we realize, for example, the point A2 P0, which correspond to this point in the space, has to be equal to match A1 P1, but also A0 P2, and the axioms of conjoint measurement guarantees, in fact, that the two different ways of reaching the same point would yield the same result. This can be described as a constructive design, in which we select levels with heavy use of solvability axiom in order to match or solve the equation. Many designs in the social sciences, however, are not constructive in character. In fact, constructive designs can be found very rarely outside psychophysics and decision theory, where we deal usually with graded and often continuous attributes, so that such constructions can easily be carried through. Most experiments in the social sciences have a factorial structure of the type described here. One usually starts with a product set, say A cross B, with several finite number of levels on each factor, and then obtains some measure of the effect of each of these cells. And the question is, under what condition can we find a additive representation for such a factorial structure? Note that in such a structure, typically we do not have whether in principle the structure is solvable or not is beside the point, because the data we obtain does not permit us to carry out the construction described here. So we are stuck, so to speak, with a particular data matrix and would like to know whether such a data matrix can be described in an additive form. Today's lecture will focus and present a solution to that problem. Before we address the general problem, however, it is important to note a problem that arises and that will provide some motivation for the present development. What we have here on the board is an example of a 3 by 3 by 2 factorial design, in which the factors are labeled 1, 2, and 3, and the levels of each factors as A, B, and C. So we have two factors, 1 and 2 have 3 levels each, and the third factor, 3, has 2 levels. So what the numbers in the cell represent the rank ordering of the effects obtained in that factorial experiment. And I'd like to call your attention to the following interesting fact. Remember from earlier lecture on conjoint measurement, we have learned that if a structure of this type, three-dimensional structure, factor structure, satisfies the independence condition as well as the solvability and the Archimedean condition, it has an additive representation. It is easy to verify that the structure described here does in fact satisfy the independence condition. What it means, in effect, is that all slices of this structure, of this cube, if you wish, are ordered in the same way, and it's easy to verify that indeed they are. To take an example, we have here 1, 5, 7, 2, 6, 8. If we take a slice along the vertical side, we have 1, 2, 3, 4, 11, 12. If we take a slice here, we have 11, 13, 17, 12, 14, 18. And it's easy to check that this structure does satisfy the independence condition. Nevertheless, even if the testable property of independence is satisfied in the data, and even if solvability is satisfied in the data generating, in the population from which this result is viewed as a sample, we still may not have an additive representation for this particular structure. And the reason is that the cancellation condition is violated, as can easily be seen because by the following drawing. This cell is greater than this cell is greater than this cell, but this cell is greater than this cell, contrary to the cancellation condition of additive conjoint measurement. Consequently, we do not have, there is no additive representation for this structure. To examine the situation more carefully, let's convert these rank orders into measurement inequality. To economize on notation, let's use prime, so A prime 1, to stand for phi of A1. So A1, A2 are the various level, A1 prime are the additive scale values associated with our solution. Now, since the B1 C2 combination exceeds the A1 B2 combination, we have B1 prime plus C2 prime greater than A1 prime plus B2 prime, and so on. Since the C1 B2 combination exceeds the B1 A2 combination, we have this inequality, and we have the third inequality corresponding to the A1 A2 combination exceeding the C1 C2 combination. It's easy to see, however, that if we were to add the three inequalities, we'll find a contradiction because the sums are in fact the same. So we have a result of the form sigma greater than sigma, the reason being that the sum on the left includes A1, B1, C1, A2, B2, C2, all of those primed, of course, and the sum on the right also includes A1, B1, C1, A2, B2, C2. Hence, we have a contradiction, and therefore no additive solution could be constructed for such a matrix. The point of that detour is that it is not sufficient to check the necessary condition, even if the solvability assumption could be safely assumed. The reason is that in the presence of solvability, the independence condition implies the cancellation condition, which is violated in this case. Hence, if we are willing to buy the solvability axiom, this data should be viewed as an evidence against independence, even though it is satisfied in this data. This example shows, I believe, the subtlety and the care that should be taken in testing axioms, and further motivate the development of a test of necessary and sufficient condition for a particular finite set of data. Okay, now we have observed the solvability condition described here has a character that two inequalities in the data implies a third one. We have noted earlier an even more simple condition, which we call an independence condition, which says in effect that if AP is greater than BP, then AQ should be greater than BQ. This is a case in which one inequality implies a second one. Here we have a case in which two inequalities imply a third one, and here on the left we have another example of a necessary condition for additivity in which three inequalities, 1, 2, 3, imply a fourth one described by a double arrow. And in general, as you might guess, the situation could get worse and worse. As the matrix gets larger and larger, we'll pick up more and more cancellation condition, and in fact we can describe this as a third order, fourth order cancellation condition. This would be a second order cancellation condition, and independence will correspond to a first order cancellation condition. And in general, as we look at larger and larger matrices, we'll pick up more and more higher order cancellation conditions that are not derivable from the lower order condition, so the picture gets more and more complicated. In fact, the reason Scott and Suppes, in an important paper in 1958, have proved in effect, or have shown in effect, that it is not possible in general to give a finite list of cancellation conditions of this type that will hold for any finite n, the reason being that you can have a set of n inequalities in which every set of n minus 1 inequalities are solvable, but the addition of the last inequality would make the system insoluble. This was the state of the art for several years, and it seems like primarily a negative result. But of course, it is possible to obtain a necessary and sufficient condition if we were to generalize and to develop an axiom schema which will encompass essentially all orders of cancellation. And this is the work that I'd like to describe right now. Much of this work has been developed independently by a mathematician, Bob Aumann from Jerusalem, a logician, Dana Scott, a philosopher, Ernie Adams, and a psychologist, myself. And all this work has appeared around 1964, which work was done more or less independently. Okay, in order to describe a necessary and sufficient condition for additivity for finite set, certain constructions have to be carried out. Let us start with, let A be a finite product set of the form A1 cross AN, where all the sets are finite and AI and AJ are disjoint. As is often the case, let us assume that we have a strict partial order on A. Let me stop here and note that in this lecture, I would assume that the order relation is always strict. Namely, we have no inequality, we have no equalities, we have only strict inequalities. This is usually the realistic case with data, because rarely, if ever, do we obtain two conditions that produce exactly the same response. So in this case, we can assume that all the inequalities are strict. If we were to include inequalities, that wouldn't change the theory much, but will introduce a few complications that I'll just as soon ignore for the purpose of this lecture. So we assume that this relation is a strict order. However, we do not assume that it's necessarily connected. So A and B, A may be greater than B, B may be greater than A, or A and B may be incomparable. Okay, let us suppose that each one of those AI, when I goes from 1 to n, has ki elements, and let k be the sum of all the ki from 1 to n. Next, let's form a new set, which we'll call capital Y, which is a union of all the AI. That is, this is essentially the union of all the levels in our design, and naturally it has k elements, which will denote y1, y2, up to yk. In the example that we have considered before of the 3 by 3 by 2 design, our capital set Y will include A1, B1, C1, A2, B2, C2, A3, and B3. So this set will include 3 plus 3 plus 2, 8 elements. So Y, in effect, is the union of all the condition of all the levels of our design, and Y1 through Yk are its elements. Next, we define a one-to-one map from A is in fact our product set, to the reals to the k power. And the mapping is defined as follows. For any A, any element, any cell in our matrix, or any element in our product set, we'll define A bar to be a vector with k components, denoted A1 bar up to AK bar, where A bar L, where L goes from 1 to k, is defined to be 1 if YL is a component of A and 0 otherwise. So in a way, A bar could be viewed as a characteristic function of A. It simply tells us which levels are included in that particular element. Hence, each A bar where A is an element of A, is a vector over 0, 1. The components are either 0 or 1. It's with K, the K vector over 0, 1. Let A bar be the set of all those vectors, so it's a set of all A bar where A is an element of A, and A plus be the additive closure of A. What we mean by an additive closure is simply all vectors that could be obtained by adding vectors in A bar, where addition is defined normally component-wise. Put differently, A plus is a minimal abelian semigroup that includes A bar. Once we have constructed this set, A plus, we can define now a new relation which we'll call greater sub 1 on A plus, and the relation will be defined as follows. We'll use lowercase xy to denote element of A plus. Remember that the set A plus is a set of k vectors whose elements are now not 0, 1, but positive integers, since it is obtained by sums of vectors whose elements are 0 and 1. Now we're going to define x to be greater sub 1 than y if and only if the following conditions hold. First, x is expressible as a sum of element a1 bar up to am bar, where the a's, of course, are elements of our product set. Y is expressible as a sum of m other vectors, b1 bar up to bm bar, and for every j between 1 and m, a superscript j is greater than b superscript j. So the relation defined on A bar, on A plus, is essentially the extension of our original order relation defined on the elements of A. So we say that one sum of vectors is greater than another sum of vectors if the vectors could be paired such that a strict inequality holds in every case. The major result of our lecture today, that I will discuss in a minute, is that the requirement that this relation be irreflexive, that is, we cannot obtain x greater sub 1 to x, is both a necessary and sufficient condition for the solvability of the system of inequalities, and in the same way it's a necessary and sufficient condition for an additive representation for a product set, finite product set. And we'll turn to discuss this result in a minute. We have defined now a new relation greater 1 on this set of vectors, and we would like to show that the irreflexivity of this relation is both necessary and sufficient condition for the solvability of the system of inequalities that amounts to measurement. Let me first discuss an example to bring out some of this abstract construction to life. Let us go back to the example we had before of a product set A equals to A1 times A2 times A3, where each of the factor is binary, has two levels. A1 has A1, B1, A2, and so on. One may want to think about this as a set of commodity bundles which has two levels of each of three attributes, say bread, wine, and butter, with two levels of A each. Now, let us suppose for a moment that we are interested in the construction of an additive representation for such a structure. We have the usual ordering relation, which we have assumed to be strict, over this 2 by 2 by 2 set. Let us suppose now that we have a failure of independence. This is diagrammed here because we have A1, A2, A3 is greater than B1, B2, B1, A2, B3, but B1, B2, B3 is greater than A1, B2, A3. This is a failure of independence, as you can clearly see, because the first inequality implies that the combination A1, A3 should be greater than the combination B1, B3, whereas here we obtain the opposite conclusion. B1, B3 is greater than A1, A3. The middle component is the same on both upper and lower inequality. Let us see what I'd like to show, how the condition of the irreflexivity of this induced relation implies independence. And in fact, to show it, let's go back to this set Y. And remember, Y is essentially the union of A1, A2, A3, which in this case, it consists of all 6 levels, A1, A2, B1, B2, C1, C2. This is our Y. Since each factor is binary, K equals 2 plus 2 plus 2, or 6. So first we form the union of the level, which in this case is a set Y. Next, we represent now each of those 4 cells as a vector, as a 6-dimensional vector over 0, 1. And in particular, it will be convenient to adopt the following notation. We will use whenever each variable takes a value 1, we'll write it as a 1, 0, and otherwise we'll write it at 0, 1. So in particular, the combination A1, A2, A3 will be represented by the vector 1, 0, 1, 0, 1, 0. Okay? And therefore, the first inequality, data inequality here, translate to the vector inequality that 1, 0, 1, 0, 1, 0 must exceed, which is a vector associated with A, must be greater, using this definition, with just one sum, than 0, 1, 1, 0, 0, 1, which is a vector associated with C, and similarly, the vector associated with B should be greater than the vector associated with D. So far, it's just a notation explaining the vector notation and translating data inequality into those inequalities on the vectors. Now, we move to A+. A+, remember, is the sum of those, and now we can add the vectors. Therefore, the sum of the vectors associated with A and B is simply 1, 1, 1, 1, 1, 1, which can be easily seen if we'll just perform component-wise addition on this vector. Similarly, the sum of the 2 vectors associated with C and with D also produce 1, 1, 1, 1. So the sum of those 2 vectors produce the same sum. But since we have obtained this order, we obtain that vector is greater 1 than itself, which contradicts the reflexivity of greater sub 1. What we have shown, in effect, then, that whenever we have a violation of independence, it implies a violation of the irreflexivity of greater sub 1. And in fact, it's possible to show that the irreflexivity of greater sub 1 implies all cancellation of all orders. So this is a kind of summary of all the necessary conditions that we have discussed earlier in this lecture. And you are invited to try and check to show how you can derive many of the cancellation and independence conditions discussed earlier in our lecture from the irreflexivity of this relation. To show that the irreflexivity, there is a slight mistake, this should be irreflexive. To show that this relation must be irreflexive, let's assume that there exists an additive representation phi. If such a representation exists, then in particular, if X is a sum of some characteristic vectors, which could be decomposed as sum of some A's, but also as a sum of some B's, just as we have seen here, then it follows that phi, the sum of the solutions of those elements, must be equal to the sum of the solutions of the B's. But if we have x greater sub 1 than x, which is a contradiction of the irreflexivity of greater sub 1, then we must have a contradiction somewhere, because those two sums cannot be both equal and unequal. This argument in this example meant to demonstrate the necessity of the irreflexivity of greater sub 1. As it turned out, and the major result of the work on measurement inequality, is that this condition is not only necessary, as can be readily seen, but it's also sufficient for having an additive representation for a finite product set. This leads us to the following theorem. And the theorem says that greater sub 1 is irreflexive if and only if there exists a real valued function phi on y. Remember, y is a union of all the level. It's a set of all the unknown in our measurement system. And another function psi on a, such that the following two conditions are true. First, psi of a, and remember, a now is an element, is a cell in the matrix, if you wish, with component a1 through an, could be written as an additive combination as a sum of phi of ai. This is the usual expression of additivity. Secondly, this representation is order-preserving in the sense that if a is strictly greater than b, then psi of a is greater than psi of b. This was not formulated as an if and only if here, because we have assumed that this relation may be only partial, not all two elements are comparable, which is a slightly more general result than the result we have for the normal treatment of additive conjoint measurement. Now, the proof of sufficiency, which I will not give in full, but just try to describe the essential step in the major concept, is composed of several parts, and primarily it reduces this problem to a standard problem of solving conditions for the solution of systems of linear inequalities. First, let me point out that in order the proof of sufficiency demonstrate, essentially, in order to prove sufficiently, it would be enough to show that there exists a vector z in Re to the k, is vector k component, such that whenever A is greater in the order than B, then the dot product, or the scalar product ZA, would be greater than the scalar product ZB. To refresh your memory, the scalar or the vector product ZA is simply the sum of ZI AI. Remember, Z now is a solution vector that we are searching for. A is a characteristic vector of an element A, which is, as you recall, 1 for all the elements, for all the levels that are included in A, and 0 otherwise. If we can find such a vector, that is, if we can solve this vector equation for Z, then we can simply set phi of YL to be ZL. We simply can take the solution, the scale value, to be the appropriate component of this vector, and then by the definition of A bar, which is this characteristic vector, simply the sum of all the phi of AI, which is by definition psi of A, is simply the vector product Z, or dot product Z times A bar. What all these remarks mean is that if we could find a vector Z which solves this equation, we are through, because then we can directly translate it into the solution that we want. Which means now that our real problem is to characterize precisely the condition of solvability, or the condition for the existence of such a vector Z. In order to do this, to understand the problem, we should turn to the issue of solving systems of linear inequalities. Let me just very briefly illustrate how our measurement problem is directly reducible to the problem of solving systems of linear inequalities. Going back to the example of a 2 by 2 by 2 design, and let's take the particular independence, the particular data pattern observed here. We can translate that directly into inequalities in the following way. Using, again, to economize our notation, instead of phi of A1, we'll just write A1 prime. So we use prime here to denote scale values as opposed to, so A1 is a level of a particular factor, A1 prime is a scale value, the unknown scale value associated with that level. Okay, so the inequalities we had before simply translate into the equation A1 plus A2 plus A3 with prime greater than B1 plus B2 plus B3, and so on, B1 plus B2 plus B3 greater than, and so on. And now if we simply, since all the coefficients in these equations are integers, and since we don't have constant in this case, we could simply subtract all the inequalities on the right from the inequalities on the left, and write these inequalities in the form, put a minus here, and write that in the usual familiar form of homogeneous inequalities. So in order to obtain an additive solution for our data matrix, we are essentially trying to find a solution for systems of homogeneous linear inequalities with integer coefficients. Written more compactly, we can represent the system of inequalities in this form. Namely, we are trying to solve for the sum of alpha ij zj greater than 0 when I ranges from 1 to m. Now, the alpha ij are integers, and the zj are the unknown scale values that we are trying to solve. At this point, to get a better intuition for the solvability problem, it would be useful to switch to a vector notation and rewrite this equation as it's usually done in vector notation. So let z, as before, be our solution vector that goes z1 to zn, and alpha I would be the coefficient vector with component alpha I1 up to alpha In. Remember, the coefficient vectors is what we get from those inequalities, which in this case are all 1 and 0s. Using this notation, we can rewrite now our system of inequalities in the form that appear here. Namely, we are looking for a vector z such that the dot product z with alpha I would be positive for all I. Remember that alpha I is a vector now, not a number. And again, this is a dot product which we have defined before, namely the sum of the cross products. In this form, so essentially we're looking for a vector z such that its dot product with the whole set of alpha I vectors are all positive. Now, at this point, the problem has a simple geometric representation. Recall from elementary mathematics that the dot product of a vector z with another vector is positive, negative, or 0, depending on whether the angle between them is acute or not. So in particular, the statement that z, the product of z with each one of the alpha, is positive is equivalent to the statement that z must make an acute angle with each one of the alpha I. Therefore, to find a solution for this system of inequalities is equivalent of finding a vector z which makes an acute angle with a set of vectors alpha 1 through alpha I. So we have reduced our problem to this situation. Let me try to use a drawing in the plane to illustrate the problem. In general, we'll be dealing with a higher dimensional space, but much of the ideas could be conveyed by this simple drawing in the plane. Let's suppose these are our 4 coefficient vectors, alpha 1, alpha 2, alpha 3, and alpha 4. And the question we are asking is, could we find some vector z somewhere in this space so that it will make a right angle, an acute angle with each of the 4 coefficient vectors. First of all, it's kind of obvious in this picture that we can probably do it, and any vector z that we'll draw, say, someplace here, will have that characteristic of forming an acute angle with all those alphas. More generally, the angle, of course, is taken through the origin. So it is this angle that we are looking at. Now, note that there is an obvious necessary condition for the solvability of this system. If a solution vector z to this system exists, then it should be possible to find a separating plane, which is drawn here as a heavy line, and more generally, in higher dimension, a separating hyperplane through the origin, such that all the alpha vectors lie on the same side of that plane. The reason why this condition is necessary is that if such a plane would not exist, namely, we will not be able to separate, to pass a line, in this case, through the origin, all the alpha will be on one side, then it should be impossible to find a z which will make an acute angle with all of them. It would mean, in particular, that the angle between some alpha will have to be here, and another alpha will have to be here, and then any vector in between could not simultaneously make a acute angle with all those alphas. So it's a necessary condition that we can have a separating line in this case, or a plane, or a hyperplane in the more general case, so that all the coefficient vector, all the alpha, will lie on one side of it. And indeed, the major result for solvability of system of linear inequalities asserts that this condition is both necessary and sufficient. Namely, the system has a solution if and only if such a separating plane exists. Note now that if a separating plane exists, through the origin, of course, 0 must be outside the origin, the 0 vector, must be outside the polyhedron formed by the alpha. The polyhedron formed by the alpha, if we'll take these vectors as the vertices and form a polyhedron by combining with straight lines, using straight line to combine the vertices, using the coefficient vector as the vertices of that figure, it's clear that if a separating plane exists, then 0 must be outside that polyhedron. Conversely, if 0 is outside, then we can pass a separating hyperplane. The reason for that being that if we were to choose, if 0 is outside that polyhedron, we could take the point on the polyhedron that is closest to 0. And that will be some point, say, here. And it's not difficult to see that this point could be is a solution vector z. The reason being is that through this point, that since the solution space is convex, through this point we can pass a hyperplane so that the polyhedron would be completely on one side of it, and it would be parallel, and we can pass a parallel hyperplane through 0. Consequently, what that intuitive discussion meant to illustrate is that a necessary and sufficient condition for the solvability of the system is that 0 should be outside the polyhedron formed by the coefficient vector as vertices. Let me try to state it now more precisely as a formal theorem. And the theorem, which is quite basic in the theory of linear algebra, says the following, that the system alpha I z greater than 0, when I goes from 1 to m, has a solution if and only if the convex hull of alpha 1 through alpha m does not include 0. The notion of a convex hull, of course, is the set of all mixture convex combination of elements from of these vertices. And more precisely, that is, if and only if there are no numbers, non-negative numbers, lambda 1 through lambda m, all non-negative, so that they add up to 1, such that the sum of the lambda I alpha ij is 0. So a necessary and sufficient condition for solvability, again, is that the origin, 0, could not be expressed as a convex combination of the elements of the coefficient vectors, and it's not easy to show that this condition essentially is equivalent to the irreflexivity of our relation greater sub 1. This is essentially the major result, and I would like to conclude with some general remark about the implications of this result and its extension. First, let me mention that although we have obtained a mathematical solution to the problem, the solution in many ways is less satisfactory than the kind of axiomatization that we have obtained with other measurement systems, and the reason is that the condition of the irreflexivity of greater sub 1 is not exactly transparent, and it's not directly testable. It summarizes essentially the many testable conditions, all the testable conditions that are needed, but in itself is not very transparent. Nevertheless, it does provide us with some insight about the systems under study, and in many situations, the understanding of this condition could be very useful. Secondly, the uniqueness, as one might expect in this case, is quite different than the stronger uniqueness condition obtained with the presence of solvability axiom. The solution that we have here is not unique up to a positive linear transformation. On the other hand, it's not an ordinal scale either. Rather, the uniqueness property of the solution is given by essentially the uniqueness of the solution to the corresponding system of linear inequalities, and it is essentially obtained by characterizing exactly this polyhedra. So the solution space is what's sometimes called in the psychological literature an ordered metric scale, namely the set of all solutions to a system of linear inequalities, which amounts to a convex polyhedra of that kind, and which could be characterized in terms of the vertices. So any convex combination of the vertices is a solution. Finally, the present results could be extended in two directions. Let me briefly mention one. The first is that throughout this treatment, I've assumed that all our data inequalities are strict. Therefore, our system of inequalities involve only strict inequalities and no equations. The results readily extended, and in fact, the original form of the result includes treatment of systems that involve both equations and inequality, and the treatment is slightly more complicated, but in principle, the same result and the same logic applies. The second extension is that this result could readily be used to apply not just to additive conjoint measurement with any finite number of factors, but also to many other representations such as probability, difference measurement, and many other linear representations. Finally, the result could be extended much further to apply to polynomial measurement inequalities too, in which the inequalities are no longer linear, but they involve a multiplication as well. The results, of course, are somewhat more complicated. The condition is very similar. In this case, too, we form the union of all the levels, and the irreflexivity of the relation is still the necessary and sufficient condition, except that this time it has to be done in terms of the extension of the relation, so the result is still more complicated and less applicable to direct tests.